Good afternoon again, everybody. We're going to get started here with the Exam 3 review. If you just joined us, you probably don't have time to do the question, but that's okay. You can hop in for the next one. Calculate the predicted atomic radius for selenium given the atomic radius of sulfur and tellurium. If you had a chance, give me your answer. A, B, C, D, or E. And if you're looking at the question like, I have no idea, you can write help. So everybody's just chiming in with an answer. We're saying C. And I'm going to agree with that. Here's why. So if you look at a periodic table, the order of the elements for group 6A, you've got selenium or sulfur, then selenium, then tellurium. And we're told the atomic radius for 2 of these elements, and we're trying to guess the one in the middle. We know for our trend in general for atomic radius, as you go up a group, you're going to increase. So that means that the radius for selenium has to be smaller than 143 picometers, but it's got to be bigger than 104. So it's somewhere in between. The only answer that fits that is 124 picometers. So how do we feel about that question? I know a few of you got it right. Maybe if you didn't have a chance to do the question, does it look like something that would make sense to you if you had a minute to do it? All right. And I'm just pulling these directly from the Exam 3 review that I posted already. So if you had a chance to look at that over the weekend, then you should be good. So this next question, you've got to write the noble gas configuration for the following neutral atoms and ions. I will give you 4 minutes. Make sure you're looking at your periodic table and figure it out. And then I'll start writing in some answers. Are we ready to go over this question, or do we need some more time? Oh, okay. We're hitting with the answers. Don't worry about trying to put it into the chat, because that's a lot. So we'll go over it and then you can check your work. Thought I gave myself enough periodic table, but I didn't. So I just got to draw in a little bit. Okay. So we're doing the noble gas configuration because that's what we covered in Chapter 5. So you'll still need to understand the full electron configuration for the final exam. But for Chapter 5, you'll only need to be able to write the noble gas configuration. For iron, we're in period 4, which means we're going to use the period 3 noble gas. That's argon. Now we have to fill in everything between argon and iron. That's the 4s2. And then 3d, you count 1, 2, 3, 4, 5, 6. So that's what you should have for iron. And yes, Finelli, that's right. Now this second one, we're looking at an ion. We're looking at phosphorus. It normally has 15 electrons when it's just the phosphate or the phosphorus atom, the neutral atom. But if we add on 3 electrons, which is what the 3 minus implies, now we've got 18 electrons. The other element that has 18 electrons is argon. So that's the configuration for the P3 minus. That's the phosphide ion. How do we feel about that one? Did we get that one right? Okay. I'm going to do a different color for barium just to break up the black. So we're looking at the barium ion. Barium is in period 6. When it loses 2 electrons, it becomes the barium ion, Ba2+. So it's going to look like the noble gas that came before it. So you look at the period before barium. Barium's period 6. We need to look at period 5. So that's xenon. Yes, what's your question? So when it comes to the ions, it's always going to be just a noble gas, and you have to figure out which one. But let's say I asked you cesium. It's going to be the same answer because cesium has 1 valence electron. It loses that to become the cesium ion, and it will also look like xenon. Does that make sense? Yeah, so let's say that we had cesium. The cesium ion, it will lose its valence electron to become cesium plus. Its noble gas configuration will also be xenon, the same thing as the barium, because they're both losing the electrons in the 4s or in the 6s orbital. No. Yeah, for the ions, it's just going to look like a noble gas. You're welcome. Now let's go and do arsenic. So that's a neutral atom. We're going to start with argon because that is the noble gas that comes in the period before it. Now we've got to fill in everything between argon and arsenic. That's 4s2, 3d10, 4p3. So as Patrick said, for these neutral ones, you're going to have more than just the noble gas. You're going to have something else coming after it. But for the ions, you're just going to have a noble gas, and you have to figure out which one it is. So how do we feel about writing these noble gas configurations for ions and atoms? Yeah, go ahead. So arsenic is a tricky one because it's a semi-metal. So we're not telling you rules for that because semi-metals don't play by the rules. So arsenic is not a good example for this class. Yeah, so don't worry about those. Only worry about the metals like the group 1 and group 2, group 3, like aluminum. And then the non-metals that we talked about. So everything over here. Outside of that, I'm not going to ask you anything. Alrighty. Oh, yeah, go ahead. Mm-hmm. I will specify noble gas configuration. Is that what you mean? Versus the full configuration? Yeah. And so for chapter 5, it's just the noble gas configuration because that's what we worked on. The full configuration was in chapter 4. But on the final exam, I will tell you which one. Alrighty. Good questions. So here's some review from chapter 6, which we covered last week. Now I changed the question a little bit. On the exam review, I didn't have you classify, but here I am having you classify just so we can get classification and writing the chemical formulas all in one question. So I will give you another 3 minutes to get started on this, and then I'll check in to see if you need more time. All right, y'all, we're going to get started. So I don't want you to write your chemical formulas in the chat, but you can definitely write your classifications. And we can use the same abbreviations as before. So letter A. What kind of compound do we have here for zinc carbonate? So I'll give everybody a warning. I think somebody's mic is on. I'll give you a warning. If you can't do the chapter 6 naming and writing chemical formulas, then chapter 7 is going to be struggle bus. Like complete and total struggle bus. Because you need to be able to classify and write chemical formulas. So I agree, A is a ternary ionic compound. We've got a metal plus one of those polyatomic anions. What kind of compound is B? Tin 4 chloride. So it's a binary ionic compound. Metal plus a nonmetal. What about the last one in C? What do we have? It's a binary molecular. We've got 2 nonmetals. So now I'll go through and write the chemical formulas so you can check your work. So zinc is a transition metal, but there's only one ionic charge that it can have. It's an exception. Zinc is always 2+. Carbonate you can look up on your common ion sheet, and that's CO3 2-, and you'll get that sheet for the exam. Don't need that 2- there. So that should be your chemical formula. For tin 4 chloride, we're told what the charge is because of that Roman numeral there. So tin is 4+. The chloride ion comes from chlorine, which is Cl. And you can figure out the charge for that anion by taking the group number -8. It's in group 7A, so 7 - 8 gives you -1. So you've got a negative here. To make the charges balance, you have to have 4 chloride ions. So that should be your chemical formula there. The last one is probably the easiest because everything you need is right there in the name. The first element is nitrogen. The prefix di tells you that you have 2 of them. So you put a subscript of 2 for the nitrogen. Pentoxide. The ox is the first syllable of the element that is the second element. That comes from oxygen. And pent is 5. So those are the Greek prefixes that you need to know for naming the binary molecular compounds. So how do we do on that? Okay, Finelli, I see your question. So zinc 2+. It's not zinc with the 2 because zinc is an exception. There are 3 exceptions. Yeah. Your mic is still on, Finelli. Just letting you know. So you need to remember those exceptions for the transition metals. Zinc, cadmium, and silver only have the 1 ionic charge. So you do not need to use the stock system there. Any questions on this one? Then we're going to move right along. So you'll get more review of Chapter 6 as we cover Chapter 7, because we're going to be doing a lot of naming and writing chemical formulas from the names. So don't worry. There's also a practice sheet for naming and writing chemical formulas in the Chapter 6 folder, along with the answer key. So you can use that to practice if you don't feel particularly strong, because we didn't cover any binary acids or ternary oxyacids in that last one. Just to give you a few exam details, you're going to see a folder with exam 3, just like all the other exams. You're going to get a periodic table, as usual, same one, and that common ion sheet. So you do not need to memorize the polyatomic ions. You just need to know how to use the chart. And of course, exam 3 will be in there. So remember to open up Blackboard and Respondus when you're ready to take the exam. Print out your reference materials before you do that. The exam will go live tomorrow, and it'll disappear Friday right before midnight. What's your question? Yeah, I can hear you. Yeah. So I covered that. I covered that in the video some, and those aren't super important. I will take a look at it to see how many questions there are, because I didn't want you to have exposure to it. But I'll look at it, and if I feel like it may have, really greatly impacted your grade, then I will change it for everyone to either make it for less credit or extra credit. So I will look at the ones for the Latin naming, and if I feel like it may have been a little too difficult or something like that, then I will adjust it. You're welcome. Any other questions about logistics for exam 3? So it's the same setup. It's covering chapters 5 and 6. We've got one more regular exam to go that will cover chapters 7 and 8. Then you have the final. So as always, oh yeah, go ahead. What's your question? Yes. So you will have that week of Thanksgiving is pretty much yours. I know technically the last day of class is like that Tuesday, the week of Thanksgiving. But let's be real, nobody's going to be in class on that day. I won't be. So go home, enjoy yourself. After that week, you've got another week. And that's the week that you should be studying, because the week after that is finals week. That's when you're going to have your exam. No, the week after that week. So think about 2 weeks after classes end. I don't remember exactly what date that is. I want to say it's somewhere like the week of December 7th. Let me quickly look at a calendar. Yes. So Monday, December 7th, that's the start of finals week. And I'm going to make your final exam available for that week. You're welcome. Okay, I saw another question about a midterm exam. No, we have an exam around midterm time, but we do not have a designated midterm exam where you're tested on the material from half of the course. So the midterm grade that you receive is just going to be what your grade is as of that time. So it will include your exam 3 grade and the mastering chemistry and the chapter check-ins that were all due before that. All right, any other questions? All right, it looks like we're good. So I will remind you, at some point I'm going to have a baby. Dr. Hefner does all the things. I will keep you posted and let you know what's going on. But when that does happen, I'm going to need a few days. But don't worry, it will be planned. Yeah, so I am scheduled to have a baby. I've had 3 others, so this will be scheduled, fortunately and unfortunately. So November 4th, I'm going in. So we still have class that week. We will have class, but I will not have office hours that week. So we'll have class on the 3rd, and then the rest of the week, I will be silent, have my baby, enjoy my family, and then come back the next week. But I will remind you guys, I will adjust the homework and stuff to make sure that you don't have a time where homework is due, but you can't access me for questions. So don't worry about that. I'll keep you posted as we get closer. But just throwing it out there, since we're talking about the final exam, that's coming up too. All right. Chapter 7. Now, I'm sure y'all didn't really have a chance to look at Chapter 7 because you're probably focused on Chapters 5 and 6. Totally understandable. So we're going to go through and hit on the major concepts, but you'll still need to go through and look at the Chapter 7 YouTube lecture to make sure that you get it all. That lecture started off with going over chemical changes and physical changes. I'm not going to do that here, but I am going to give you some observations that indicate a chemical reaction is taking place. You don't have to observe all 4. You need to just see one. One observation that you can see is a gas being produced. It doesn't have to be crazy fizzing, but it can be just kind of light fizzing to, a lot of bubbles forming. So an example of that would be adding magnesium metal to an acid. You drop in that little piece of metal and you see all of this bubbling happening up here. That's the release of hydrogen gas. So that shows a chemical reaction is taking place. The second thing you might see as a result of a chemical reaction is an insoluble solid forming. That's also called a precipitate. So you may have 2 substances that are dissolved in water, which is called an aqueous solution. You have those 2 substances in their own separate little beakers or flasks, and you pour one into the other, and then all of a sudden you've got a solid forming. Again, that solid is the precipitate, and it's evidence for a chemical reaction. The third piece of evidence you might see is a permanent color change. That color change shows you that you've made something new. So a lot of the transition metals, when they are in solution as an aqueous substance, they have very pretty colors. So you might see a pink or like a magenta, green, blue. So if you see that forming after you add 2 things together, you know that you've just observed a chemical reaction. The final piece of evidence that might tell you you've observed a chemical reaction is a change in energy. Some reactions, when they occur, they release a lot of heat. That kind of reaction is called an exothermic reaction, and you'll need to know that word. An example I can give you is if you mix an acid and a base and you touch the flask or the beaker, it will get warm. It is an exothermic reaction. Other reactions require heat, and they take that heat from the environment. So when you mix those things together, the flask or beaker will get cold. That's an endothermic reaction. So it absorbs heat from the surroundings. Feeling the heat change is an energy change. And that shows you that you have observed a chemical reaction. So let's just do a quick check-in to make sure that we got it. If I mix baking soda and vinegar and I see bubbles forming, is that a chemical reaction or no? That's a chemical reaction. I'm going to put CR for that. What about cooling carbon dioxide down to form dry ice? Chemical reaction or no? It's not a chemical reaction. That's just a change in state. So if we're going from a gas to a solid, we're not doing any chemistry. It's still carbon dioxide. So it is not a chemical reaction. What about 3? 2 liquids are combined and in green precipitate forms. Yes, that is a chemical reaction. So you're seeing a new solid forming and a new color. So that's evidence that you've just observed a chemical reaction. So any questions there? It's a pretty simple concept. The only tricky ones are ones where you have a change of state that might seem like it's a change in energy, but it's not. So are we good there? Let's move on. Now I'm going to give you some information so that we can build up to writing chemical equations as words or written description. This table has chemical equation symbols that you will encounter. And I'll go over these a little bit so that you understand what they are. The first one is just an arrow. And you can read it or interpret it as saying produces, yields, gives. And you see that arrow between the reactants and the products. The reactants, you can think of those as like the ingredients. So if you're going to bake a cake, your reactants would be flour and sugar and butter. If it's a chocolate cake, maybe some cocoa powder, or maybe you're using melted chocolate. Those are the ingredients. That's the reactant. So in a chemical reaction, all the things that you're going to need to make something. Your products are just that. It's what you make at the end. So you're making some new compounds. In the baking example, it would be your cake. Because a cake is very different from just a bunch of flour and butter, right? You wouldn't want to eat just a plate of flour and butter. But you turn that into a cake, that's a different story. The next symbol is a plus sign. You see a plus sign in between the reactants and the products. So it separates them. So that's just an example. You may also see a triangle above that yield sign. That triangle is kind of like the Bunsen burner flame, so it means adding heat. And likewise, if you see an element written above that yield sign, it's a catalyst. So it's something that accelerates the reaction, but it's not really a reactant or a product. It doesn't get changed in any way. It's just there to speed it along. I would recommend putting this table into your notebook. So if you can print it out and put it in there, or if you want to copy it down, it's helpful. The next symbol is the NR for no reaction. So sometimes you can mix two things and nothing happens. That's no reaction. So you would put NR. And I'll give you, later on, I'll show you when that might be applicable. The last few symbols talk about the states of matter. You have to indicate whether something's a solid, a liquid, a gas, or dissolved in water, which is what aqueous is. Because that greatly changes the actual chemical reaction. So again, if you're baking, there's a difference between using melted butter and cold butter or room temperature butter. You have to specify in the recipe which one you're using. It's the same thing with compounds. Indicate the state so that you get the reaction right. So are we good there? Is anybody trying to copy this down in your notebook? Let me know if you need more time or if you're ready to move on. Okay, I'll give you another minute or two. Alrighty, let's move on then. So I gave you those symbols. Now I'm going to give you another bit of information. Some elements are written as diatomic molecules, which simply means that there's two atoms. Anytime you're looking at hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, or iodine, and it's just that, the molecule, they come in a pair. You'll need that when you're writing down, say, there's a written description that uses fluorine gas. You'll need to write that as F2. So there's hydrogen, but then the rest of them form a 7 in the periodic table. So all of these are diatomic molecules. In the YouTube lecture, I put another slide that has them listed. So if you want that slide, you can go to those notes and you can print it out or just copy that one down. But this is just a bit of information that you're going to need for writing chemical equations and writing descriptions. So now I'm going to show you how to write a chemical equation in words. Oh, sure, I can go back. Let me know when you're ready. So with all that information, I'm going to show you how I write a chemical equation in words. Now, there's a little bit of creativity here because there are some phrases that you can use. Don't get too crazy, but I'll show you what I mean. Let's first break up the reaction. We've got our reactants on the left side, always, and the products on the right side. And for the sake of this, when I'm writing about the reactants, it'll be blue. Anything about the yield sign and anything else involved in that will be red. And the products will be purple. The reactants we have COS, that's cobalt metal. So anytime you see a metal like cobalt or manganese or magnesium or iron followed by an S, that just means that you have the solid metal. O2 with the G after it, that's oxygen gas. So we didn't talk about naming those things, but I want you to be able to recognize it. That's one of the diatomic molecules I was telling you about on the previous slide. So if you saw hydrogen, H2, it would be hydrogen gas. F2 would be fluorine gas, and so on. Now we've got to talk about what we make. We only have one product here. We can classify and name it. So take a minute, classify this compound, CO2O3, and write the name of the compound as well. Does anybody else have a classification or a guess for the name? I definitely agree it's a binary ionic compound. We've got a metal plus a nonmetal. For the naming, well, we've got cobalt, and that's the metal. Cobalt is a transition metal, so we're going to have to indicate its charge. And at the moment, we don't know what that is right now. O3, that's going to be from the oxygen atom. It's oxide. Remember, you take the oxygen, get rid of everything else, and replace it with IDE. But we've still got to deal with what the charge is here. If we look at oxygen, it's in group 6A. To figure out the charge of the oxide ion, you subtract 6 minus 8. So that's our charge, 2 minus. Now we've got 3 of these because of the subscript right after the O. So for our total negative charge, we've got -6. For our positive charge, how did I get 6? So you multiply the number of oxide ions that you have, which is 3, which is from the subscript here. And then you multiply by the charge of 1 oxide ion, which we got by saying the charge is equal to the group number, 6, minus 8, which is -2. So you multiply those two things together to get the total negative charge. Is that clear? So for our positive charge, We know that total, it has to be positive 6 so that we have a neutral formula. From the formula, we see that there are 2 cobalt ions. That's what that subscript means. But we need to figure out the charge. In order for the charge times the number of ions we have to equal 6, that cobalt must have a positive 3 charge. Does everybody follow that? So the name for this compound is cobalt 3 oxide. Now you believe me when I tell you if you don't know chapter 6 and chapter 7, it's going to be struggle. Because you have to be able to name these compounds. Sure, I can repeat that just the last part about the positive charge or the whole thing, Priscilla? So if you're talking about the cross method, that's when you already know what the ions are. Now you could reverse that, but that might be a little too confusing. What I did here, let me get a different color. I started by saying cobalt is a transition metal. I abbreviate that TM, transition metal. And since it's not one of my exceptions, I don't know what charge that cobalt ion is. To figure out the charge, I have to look at the anion. The anion is oxygen, and we have to figure out the charge for the oxide ion. When we're talking about anions, that charge is going to be equal to the group number. For oxygen, it's in 6A, so the group number is 6, and you subtract 8. That gives you -2. So if I have 1 oxide ion, the charge for that ion is 2-. If I have 3 oxide ions, like I do in this compound, my total negative charge is 6. 3 ions times -2 charge for each of those 3. Are you with me so far? All right. Now that we figured out the total negative charge for the formula, we know that the total positive charge has to be +6, because when you add them together, they equal 0, and that's what we want. From the formula, we see a 2 as a subscript for the cobalt. That means that whatever charge the cobalt ion has, we have to multiply by 2 to get the total positive charge. Just like we had 3 oxide ions and we multiplied by their charge, which is -2. So if we've got 2 cobalt ions and together they make a total positive charge of 6, that means each cobalt ion has to have a charge of +3. So you're dividing the total positive charge by the number of positive ions that you have. In this case, it's 6 divided by 2. Is that a little bit more clear? Go ahead. When you say switch over the numbers, what do you mean? Yeah, so what you're saying is kind of like the reverse charge method. So as long as you get your signs right, you absolutely can. And that's what I was saying. You can do that because I know, Lydia, you asked the same thing. You can do that. And if that makes sense to you, fine. But it may be a little more confusing because you've got the cross method and then the reverse cross method. So whatever makes the most sense to you and gives you the reliable answer, that's what you go with. Fair? You're welcome. Okay, so that was a detour. But that's all right. That's what we're here for. So far, all we did was name everything. The goal is to write a description of this chemical equation in words. You always want to indicate the state of matter along with each compound. For the reactants, we have solid cobalt metal. You may also just see cobalt metal, and the assumption is that it's solid. If it's anything other than solid, you would say liquid, something like that. Solid cobalt metal and oxygen gas. Those are our reactants. Now we've got to handle the yield sign. For that, you can say they're heated to yield because we see this triangle. That means heat. Or you could say heated to produce or give. So whichever word you prefer, that's what you can use. You only have to use one though, so don't give me all three. Then you write the name and the state of matter for your products. So that's writing a chemical equation in words. I like to name everything first and keep the reactants and products separate so I don't get them confused. Then when I go to write everything, I make sure that I have some kind of a description of the state of matter for each compound. Always make sure you include whether or not something is heated or something is included as a catalyst. So does that description make sense? Do you see how that comes from the chemical equation? Y'all are probably writing this down, so I'm going to give you a minute. But let me know if this makes sense. Let's try another one. What I want you to do is name all of the reactants and the products. I'm going to write out and just set things up while you name each of these 4 compounds. I'm going to get started naming these, and I'll check in to see how you did. The first one is lead 2 nitrate. You have to figure out the charge of the lead and make sure that you write it down, because lead can have multiple ionic charges. The second compound, you can name it pretty simple because it's a binary ionic compound. So you write the name of the metal and then the first syllable of the nonmetal followed by IDE. How do we do on those 2? And if you didn't have time to finish, that's okay. I've been doing this for a long time. For the products, with lead, you still have to indicate which ion you have. And it's Cl again, so chloride. And lithium nitrate. So the NO3, you can just look at the common ion sheet and get the name for that ion. So how does naming feel? Does it feel a little bit better? So now we've got to write this in words. I'll give you another 2 minutes to try to write it down in your notebook, or at least think about it, and then I'll write it out. So don't try to put it in the chat because it's going to take you longer to type it out than anything else. So write it in your notebook, or at least think about it, and then I'll write it in about a minute. So don't worry about it if you weren't able to finish writing it down. Just want to make sure you're on the same page. It's not hard. The hardest part is the naming. Then you just got to make sure you have all the bits and pieces. For the lead nitrate, lead 2 nitrate, and lithium chloride, they're both aqueous solutions. So I'm going to write that as aqueous solutions of, and then list my 2 reactants. So aqueous solutions of lead 2 nitrate and lithium chloride. For that yield sign, you can just say are combined to yield. You could also say mixed there, whichever one. Then you list your products. Make sure you include that the lead 2 chloride is solid. And that the lithium nitrate is aqueous. So writing chemical equations in words, how do we feel about that? Decent, meh, don't get it. So I'm going to put some practice up as always. But I know y'all ain't concerned about Chapter 7 right now because you have an exam. But there will be practice up and an answer key. So it will have all of this, writing chemical equations in words, going from the words to the chemical equation, and all the other things that we practiced today. Speaking of which, let's do the reverse. So you can take a written description and write the chemical equation from it. So we're just going to do one of those examples right now. The written description is in the same order as the chemical equation, just like we were writing it. So aqueous solutions of lithium iodide and silver nitrate. That tells us about the reactants. Are mixed to give. That's our yield sign. Silver iodide precipitate and aqueous lithium nitrate. Those are the products. So with that information in hand, I'll give you 2 minutes to try to write out the chemical equation from the written description. That means you're going to need the Chapter 6 knowledge of reading the name and writing the chemical formula. So 2 minutes, and then I'll write it out. Okay. I'm going to start writing this out. The reactants that we have to write formulas for are lithium iodide and silver nitrate. Wrong color. That's better. And you don't want to forget to put the state of matter in parentheses next to the chemical formula. So aqueous solution, you put the AQ in parentheses. Those are the reactants. Our mix to give, that's just the yield sign. There's nothing special there. No heat, no catalyst. Then we've got silver iodide precipitate. Precipitate means that it's a solid. And then aqueous lithium nitrate. So if you tried that, how'd you do? Anybody else try it? Okay. Good. So writing the chemical equations from the written description and vice versa, as long as you have a good working knowledge of chapter 6 and you recognize those symbols from the chart that I showed you, you should be pretty good to go. So we're going to leave that behind us. And we're going to talk about chemical reactions. Just like we classify compounds, we can also classify chemical reactions. I'm going to give you kind of the bare bones about each of these types, and then we'll talk about each one of them in a little bit more detail, but you'll definitely want to watch the YouTube video. After we finish this slide, then we'll take a short break. The first type that we're going to cover is combination reactions. This is where you're taking simple reactants and you're forming one complex product. The key here is the number, right? So we've got multiple reactants, at least 2, and only one product. You may also see these called synthesis reactions, which I abbreviate reaction RXN. Decomposition reactions are the reverse of combination reactions. You're taking one complex reactant and you're breaking that down into multiple simple reactants or products. This will usually require heat, as will the combination reactions, but it's not a necessity. So if you don't see the heat there, it doesn't mean it isn't combination or decomposition. It's just not listed. But again, for the decomposition, you've got one reactant, multiple products. The single replacement reactions, we're talking about metals here. And you have a more active metal that replaces a less active metal in solution. You're going to need to refer to what's called the activity series, which we will go over. And that tells you the relative reactivity of various metals. Double replacement reactions. You're mixing two aqueous solutions and you're making a solid plus another aqueous solution. The key is that you form a solid, a precipitate. And the final class we're going to talk about is neutralization reactions. That's where you mix an acid and a base, and you make a salt plus liquid water. Yes, is there a question? Yes. Sorry, I usually try to define my shorthand. Yeah, whenever I do that, it just has slipped my mind that I wrote an abbreviation that I did not define. So neutralization reactions, we've got an acid plus a base, and you make a salt plus water. What a salt is, we're talking about ionic compounds. So a ternary ionic compound or a binary ionic compound. That's what we're talking about there. So those are the 5 classes that we'll talk about. But for right now, you can finish getting that in your notes. This is your cheat sheet to give you a heads up on what's to come, and it'll help you classify a little bit too. It's 3:28 now. So let's take a 10-minute break. It's about to be 3:29, so we'll say break till 3:39. Alrighty. Hope you had a good 10-minute break. I got to have some water. Say hi to my family. It's always nice. But it's time to get back to chemistry. So we ended with the types of chemical reactions that you might encounter. I filled out this little cheat sheet for you, which you can put in your notes by just copying it down or printing it out and pasting it in your notebook, or if you keep a binder. Now we're going to go through each of these and talk about them in a little bit more detail. So I hope y'all are back and it's not just me. We're kind of light today. I only see 19 people in class today. It's kind of light. But we'll go on. So we'll talk about combination reactions first. And that's when we said the simpler substances are combined to make one more complex product. I've got 3 examples of combination reactions. Now, what I'm not going into detail here is kind of like the patterns of how you make certain things. I've got the generic, metal, oxygen gas. You make a metal oxide. On your homework, you might need to make a prediction as to what that product will be. So if you're given, for example, magnesium solid and oxygen gas, you should recognize that you have a combination reaction and you're going to make magnesium oxide. And the same with these other two. So if you have a nonmetal plus oxygen gas, you make a nonmetal oxide. And an example of that would be sulfur plus oxygen gas. You can make a sulfur dioxide. And then, of course, a metal and a nonmetal. So those are examples. I go over examples in the YouTube video. You'll want to pay attention to those because you may need to make some predictions about what you make in a combination reaction. So is everybody clear on what a combination reaction is and an idea of the expectations in terms of predicting a product based on what your reactants are? Thank you. It might just be you and me, Whitney. After that break, people forget they still in class. It's all right, though. Still get the same paycheck. Not enough, but, you know, it is what it is. Sure. Oops, that's forward, not back. Let me know when you're ready. All right. Now we've got decomposition reactions, which we said is just the reverse of the combination reactions. And likewise, you may be asked to predict the products for a decomposition reaction. Just know that you take the combination reaction and put it in reverse. Like I said, oftentimes you need heat to start a decomposition reaction, but you may not always see that in the reaction. So here, there's no triangle here, but there probably is heat added. So an example of a decomposition would be taking solid mercury 2 oxide, and then you heat it and decompose to make liquid mercury, which mercury is strange. It exists as a liquid naturally. And you also generate oxygen gas. So you're taking one complex reactant and breaking it down into two simple products. Questions about that? Let me know if we're ready to move on. Thank you. Let's move on. And then we have a wait. If you need more time, you got to tell me to wait. All right. So that was the first two in the list, combination and decomposition. Before we can talk about single replacement, we have to talk about the activity series. And like I said, this talks about the relative activity of metals. It's how readily one metal will replace another in aqueous solution. The activity series is listed here. Now I can't fit it all on one line on one slide, so that's why it's broken up into 3. But lithium is the most active metal. Gold is the least active metal. So every metal that comes after lithium, lithium will replace it in solution. Every metal that comes before gold, all of those metals will replace gold in a solution, and the gold will precipitate out. So just to practice using this activity series, I want you to choose the more active metal in each pair. So the first pair, we've got iron and copper. Which one is more active? Yeah, we've got iron here and copper there. Iron comes before the copper, so it is more active. What about strontium and potassium? Which one is more active? Yeah, the potassium comes first, so it's going to be potassium. And the last pair we have is lead and nickel. Nickel is up here and it comes before lead, so it's more active. This is the same concept that we're going to use when we're determining whether a single replacement reaction occurs or not. So keep that in mind. You will get this activity series for your exam 4 and the final. So do not memorize it. You don't need to. As I said before, a single replacement reaction, you have a more active metal displacing another one that's less active. So if you take iron solid, which in this image here is this rod that's coated in iron, and you place it into a beaker that has copper sulfate, copper 2 sulfate, which is a lovely blue, what you'll see happen over time is the copper will precipitate out. You'll see kind of flecks falling out of solution, and the color's going to change. That shows you, 1, that you have a chemical reaction going on, but 2, we said on the previous page that iron is more active than copper. So if copper is in solution and then iron comes around and jumps in the pool, iron is going to kick the copper out. So you form an aqueous solution with the more active metal, and the less active metal is the one that precipitates out. So let's test that knowledge and answer a couple of questions and make sure we get it. I put the activity series down here at the bottom. Will cadmium replace iron in the following reaction? We've got cadmium solid being added to iron 2 nitrate, an aqueous solution. You got to let me know right away. Wait, hold up. Okay. So I'm going to give you an extra few seconds to make sure that I don't have to keep going back, because I don't want to discourage you from taking your notes. So let's answer the first question. When you have your answer, you can put it in the chat. Will cadmium replace iron? Yeah, when you look at the activity series, you're going to find iron comes before cadmium. So that means iron is more active. Since it's more active, that cadmium isn't going to do anything. It's just going to sit there. So for a question like that, it's no reaction. So that NR that I told you about several slides ago with the symbols for chemical equations, that's where NR comes into place. What about the second one? We've got zinc solid and lead 2 nitrate. Yeah, zinc is going to replace the lead. So if zinc replaces the lead, then we need to be able to write what our products are. This zinc is going to be paired with the nitrate. Zinc is always 2+. It only forms that one ion. So the zinc goes from being a solid to being aqueous, dissolved in water. What's our other product? The other product is the lead. And that's going to be solid because it falls out of solution. Sure, I can repeat that. So we established that zinc is more active than lead. So if a solution has lead, the zinc is going to replace it. Instead of having lead 2 nitrate, we have zinc nitrate. That zinc becomes part of the aqueous solution. And that's what we wrote here. The lead is going to fall out of solution and become a solid. So that's our other product. Is that clear? You will need to be able to do a problem like this to say there's no reaction or that there is a reaction and predict the products. There will be practice for you to do this for chapter 7 that I'll post. Are we good to move on? Okay, so there's one more thing I'm going to point out about single replacements that we don't have, well, that I'm not going to take the time to go over explicitly, but I go over it in the YouTube lecture. You'll notice that hydrogen is here in this activity series. Hydrogen is not a metal, it's a non-metal. But there are some cases where an active metal can replace the hydrogen in water, or you can have a metal being added to an acid and the metal replaces the hydrogen. So look for those in the YouTube video. They're all single replacement reactions. I wanted you to be familiar with the activity series and how to use it. The YouTube video will tell you a little bit more about different flavors of single replacement reactions. Okay. Enough plug in the video, because you really do need to watch those in addition to the live lectures. We just don't have the time to cover everything in a live lecture. So we've got a couple more types. Yeah. Sure, the hydrogen statement. So hydrogen is part of the activity series. It's not a metal, but there are metals that are active enough that can replace the hydrogen in water. There are also metals that are active enough to replace the hydrogen in a binary acid or a ternary oxyacid. So that's why the hydrogen is included. And I talk about that more specifically in the video. Okay. I want to make sure we have enough time. So we've got double replacement reactions, and then we've got one more. In a double replacement reaction, you've got two aqueous solutions. You've got ionic compounds. You mix them together, and you form a precipitate, that insoluble solid. Notice how I color-coded so that you can see where the different anions end up. So the barium starts with the chloride and ends up with the chromate after you mix these two things. The potassium started its life partnered with the chromate. After you mix, it's now partnered with the chloride. Still aqueous, but we form a precipitate, something that's not soluble. This is the key to having a double replacement reaction. Otherwise, you have no reaction. So you might be wondering, okay, that's great, but how do I know if something is soluble or not? Solubility rules. These will be provided for exam 4 and the final as well. So do not memorize them. Instead, work on using the chart and learning how to use it. The first 5 rules tell you what is typically soluble in water. So compounds that have ammonium, lithium, sodium, potassium, those are all going to be soluble. Compounds that have the acetate ion, nitrate, halides, and sulfate are also mostly going to be soluble. But for the halides, there are some exceptions. Same thing with the sulfates. The bottom half of the chart tells you what's typically insoluble. Anything that you see with a carbonate, chromate, phosphate, sulfide, or hydroxide, it will very likely be insoluble. With the exceptions being those group 1, so the lithium, sodium, potassium, along with the ammonium ion. Anything that has one of those is going to be soluble. Anything outside of those is going to be insoluble for all of these different ions listed. So instead of staring at the chart, let's do a couple of examples to show you how to use the chart. We've got tin 2 chromate. That's what that compound looks like. To figure out whether this compound is soluble or insoluble, we're first going to locate the rule that talks about chromate ions. That's rule number 7. Compounds with chromates are generally insoluble, except for the Rule 1 exceptions. So we look at what we have. We've got tin. Tin is not one of the Rule 1 exceptions. So it's going to be insoluble. Try to use these rules and figure out whether lead-2 acetate will be soluble or insoluble. You can put your answer in the chat. And if you need help, you can just say help if it doesn't make any sense to you at all. So the first thing we need to do is locate the rule that talks about the acetate ion. That's rule number 2. So the way you read that is ionic compounds containing the following ions are generally soluble in water. And acetate is listed there. Lead-2 acetate, there's no exceptions. So we would expect for this compound to be soluble in water. So with practice, you'll be able to use the table, but it's the same idea. You find the rule that talks about the ion that you have, and then you figure out if it's soluble or insoluble. The table will tell you. You just got to know how to ask it. Yes, go ahead. Sure. So that means that lead-2 chloride, lead-2 bromide, and lead-2 iodide are all insoluble. So that X is the halogen, Cl, Br, or I. The same thing with the silver and the mercury 1. So if you have any of these metals with a halide, it's insoluble, and those are exceptions to the rule. Other questions, or are we good to move on? The last reaction type is neutralization. And that's when you have an acid and a base mixed together, and you make a salt and water. The acid is always going to have a hydrogen first. And we should know that from our binary acids and our ternary oxyacids. Always see the hydrogen first. But we haven't talked about bases. The base is going to be a metal with a hydroxide, which is OH. And when you combine those two, you make water. And like I said earlier on the cheat sheet, for the salt, we're talking about ionic compounds. So binary ionic and ternary ionic compounds. We good on this slide? Okay, I'll give you a little more time. We are reaching close to the hour, and we still have to go over balancing equations. So, here's a little bit of practice for you to go from the written description to a chemical equation. And then I'll show you kind of the first step that I use for balancing chemical equations. For time's sake, I'm going to kind of go through it a little slow, but feel free to kind of start writing on your own what this description would be as a chemical reaction. I'm going to underline using the color scheme before with our reactants and the yield and all that stuff. So our reactants are manganese metal, which manganese is Mn, not to be confused with magnesium. And we've got aqueous nickel 2 nitrate. There's nothing special going on. We're just producing something, so there's no heat, no catalyst. Our products are aqueous manganese 2 nitrate. Again, manganese is different from magnesium. You'd be surprised how many times I see that. And we've got nickel metal. What kind of a reaction is this? It's a single replacement. Single replacement takes a metal and an aqueous solution. Double replacement, you have 2 aqueous solutions. Very similar though. When you have a chemical equation and you're asked to balance it, the first thing you should do is check and make sure to see if it's balanced already, because sometimes that happens. To do that, I make a chart. So I label my reactants and my products with an R and a P respectively when I make my chart. I write down each atom that I see. So we've got manganese and nickel. We've also got this nitrate, the NO3. Since it appears together on both sides of the equation, we can treat it like one single unit. So we can count the number of nitrates versus counting the number of nitrogens and oxygens. That will make our lives a lot easier. Now we just literally count. How many do you see? If there's no number out in front, then that means you assume that it's 1. If there were a number there, it would be called a coefficient. And again, it's a 1 here. So we've got 1 manganese atom on the reactant side. Again, there's no coefficient in front of the nickel 2 nitrate. So we're going to assume that we've got 1 of these compounds. That means we have 1 atom of nickel and 2 nitrates. That subscript that comes after the parentheses means that I've got 2 of whatever came directly before it. And just like in math, where you would multiply the 2 times whatever's in the parentheses, that's what we're doing here. So we've got 2 nitrate ions. Is everybody clear on that? We're just tallying up what we have. Now we go through and do the same thing on the product side. We don't see a coefficient here, so we assume that it's 1. So we've got 1 manganese. And again, we've got 2 nitrates and 1 nickel. Well, this one is balanced already. So our work is done. The goal with balancing an equation is to make sure that you have the same number of atoms or ions on the reactant side and the product side. If you have that, then you're done. Life will not always be that easy. So let's do a real one. And so I went forward before asking, can I move forward to the next slide? Okay. This one we're going to have to balance. I'll tell you right off rip. But we start it the same way. There are only 2 atoms here, hydrogen and nitrogen. For each of these on the reactant side, there are 2. There's no coefficient here, but the subscript 2 tells us that we have 2 hydrogens and 2 nitrogens. These are 2 examples of the diatomic molecules I was talking about way earlier. On the product side, which let me label my R and my P, we have 1 nitrogen and 3 hydrogens. So we somehow lost a nitrogen and gained a hydrogen. Clearly this is unbalanced. So we need to add coefficients to balance out the number of atoms on each side. So that means that we're adding numbers in front of the compounds to balance them out. So you don't have to add a number everywhere, but that's the only place that we can add. You never want to change the subscripts. So this 2, this 2, this 3, they do not change. To balance, we're going to start by looking at our hydrogen. We've got 2 on one side and 3 on the other. We need the lowest common denominator for 2 and 3. So that's the smallest number that you can take and divide by 2 and divide by 3 and get a whole number. The lowest common denominator for 2 and 3 is 6. So on the reactant side, we're going to multiply the hydrogen gas by 3. And on the product side, we're going to put a 2 in front of the ammonia atom, or ammonia molecule, because that's where the hydrogen is. Then we're going to make another chart. After each change, it's nice to take a lay of the land and see how many of each atom you have now. So now we've got 3 times 2 hydrogens, which is 6. And we still have 2 nitrogens on the reactant side. On the product side, we're taking that multiplier, that coefficient out in front, and multiplying that by the subscript to get 6 hydrogens. And we're doing the same thing for the nitrogen. We've got 2, and we don't see a subscript there, so it's an implied 1. Now we've got 6 hydrogens and 2 nitrogens on each side. Now we're balanced. That's balancing an equation. Questions, comments, concerns? So if you've taken chemistry before in high school, you certainly have done this. I'm going to do one more example for you, and then we'll close out the class. I will have plenty of practice for this for you, so don't worry. If this doesn't make sense, or after class, directly after class, you're like, wait, completely forgot everything, you'll have practice to do. So again, I'm giving you a written description. You'll see it like this or as a chemical equation. Either way, you need to be able to balance. So in this case, we need to write our chemical equation first. Iron is heated with fluorine gas. Fluorine gas is another one of those diatomic molecules. And we're making solid iron 3 fluoride. Now that we have our equation, we have to check and see whether it's balanced. Feel free to go ahead and do it on your own as I'm doing it to see if you get it. And if you learned another method that makes more sense to you, by all means use it. But this is what makes sense to my brain. On the reactant side, we've got 1 iron atom. How many fluorine atoms do we have on the reactant side? We've got 2. On the product side, we've got 1 iron atom and 3 fluorine atoms. We're not balanced, so we've got to do something. We'll start here with the fluorine. So notice how I always choose the one that is the most complicated. In this case, the iron is already balanced in this situation, so the fluorine is the problem. We're going to need our lowest common denominator again, which is 6. It's going to be 6 a lot. I'm just going to tell you that now. Not always, but a lot. So what we're going to do is multiply our fluorine on the reactant side by 3. By placing a 3 out in front. That's the coefficient. On the product side, we have to put a 2 in front of the compound that has fluorine. Now we check it again. On the reactant side, we haven't touched the iron, so there's still 1. But now we've got 3 times 2 equals 6 fluorine atoms because of that coefficient of 3 and the subscript of 2. On the product side, we have a 2 out in front of the iron 3 fluoride. So now we have 2 irons on the product side. And 2 times 3 equals 6 fluorine atoms on the product side. Now our iron isn't balanced. So we need the lowest common denominator between 1 and 2. That's going to be 2. So we only have to multiply the iron on the reactant side. Then you're going to want to do a final check. And as you practice this, you may not want to do as many checks. But if you do it in this method, you'll always find your mistakes. For the iron, we've got 2 times 1 equals 2 because of that multiplier out front on the reactant side. Still have the same number of fluorines because we haven't touched it. And our product side hasn't changed at all since our last change. So now we're balanced. So we had to put a coefficient in front of each one of our compounds. How do we feel about balancing equations now? Still feel decent about it? You haven't done a practice yet, and I wasn't going to throw that at you. But you'll have plenty of opportunity to practice. Are there any questions? So as usual, I have a reminder slide. You've got Chapter 7 for Mastering Chemistry due on Sunday. That's the 11th. I'm not giving you a chapter check-in. You also have Exam 3, which will be available starting tomorrow morning. And it will remain available until Friday, October 9th at 11:59 p.m. Eastern Time. I have office hours tomorrow, which is Wednesday, from 2 to 4 p.m. So if you have questions on chapters 5 or 6, stop on by. The Exam 3 review has been posted along with the answer key. There's Chapter 6 and Chapter 5 practice problems. So if you have questions on any of those things, come on through, say hi, and ask your question. You can also send me a message using course messages. So if my office hours don't align with your schedule, you can still get some help. That's all I've got for you today. If you don't have any questions, you're free to go.